So we're going to start with one concept that was sort of, we overviewed it a little bit, but I wanted to make sure that we got it in a little bit more depth. And that is this whole A, B, E classification scheme. So every one of these molecules you can classify. We call them molecular types. So we can say, no, something is, an AB2, AB3, AB2E2. Let's look at what these each mean. So A is your central atom. Everything has an A. B is basically the number of other atoms bound to it. And E are the number of unshared pairs bound to it. Okay? So let's see how this plays out in a real atom. We're going to classify cyanide, HCN, using this formula. We have our central atom, which is carbon. How many different things are bound to the carbon? 2. This is that effective pairs column that you did on your lab. So this is AB2. Are there any unshared pairs on the carbon? No. So there's no E. If there are no unshared pairs on the central atom, we don't put an E in there. So this would be an AB2. Let's look at CO2. So we have once again, you've got your central. How many things are bound to that central? 2. How many unshared pairs on the central? None. AB2. What do these things have in common, shape-wise? They are both linear. And what you're going to find is that for every classification type, there's a characteristic shape. So AB2s will always be linear. This is enormously helpful when when you're asked what shape would this be, what shape would that be. And we're going to talk more about how we can get something that's linear with the atomic orbitals that we know about. Excuse me. Okay, so let's look at something like let's look at our friend here, boron trifluoride. Okay. So we have a central, A. How many things are bound to the central? 3. No unshared pairs. That's an AB3. AB3s will always be trigonal planar. Yep. Because you're getting those 3 things as far out as possible. So now let's talk about everybody's favorite, cow farts. And you didn't build this one, but you built carbon tetrachloride, which is the same exact structure. So you have an A. How many things bound to the central? 4. AB4. If you have an AB4, it is always going to take one shape. How far apart can 4 things get on a sphere? Forms a tetrahedron. Forms a tetrahedron. So AB4s are always going to be tetrahedral. Okay, so these are all things that don't have anything on the central in terms of unshared pairs. Let's look at one that's got an unshared pair on the central. And we'll start off with NH3. This is ammonia. This is the household cleaning product. This is what makes cat pee so stinky. And of course it looks like that. So we've got our central atom. How many atoms are bound to it? 3. How many unshared pairs? Just 1. As long as it's a subscript of 1, we don't have to write it. So that's just an AB3E. Now, AB3Es use the 4-hole. You use the same thing you used for carbon tet, except in place of one of those atoms now you have an unshared pair. So it's the same arrangement with 4-hole something, except one of those is occupied by unshared pairs. So these things get pushed down into that trigonal pyramidal. Because the unshared pairs sort of shove them down a little bit. Okay. AB3E is always going to be trigonal pyramidal. So, what you should be seeing is that for each of these categories, for AB3, if I tell you something is an AB2E2, you have a central atom. How many atoms are bound to it? 2. How many unshared pairs on the central? 2. Favorite example of this? It's that dangerous stuff you've all heard about. You'll die without it. It's terrible. Let me move this over. H2O. Now, what form does that assume? It's bent, because you've got those unshared pairs that are deforming what might otherwise be a linear molecule. Anytime you have an AB2E2, it's going to be bent. So for each one of these, there's a classification based on how many things are bound to it and how many electrons are there. Okay, questions, comments, concerns? S orbitals, look like little beach balls. We have the double drumsticks, the dumbbells, p orbitals. We've got the weird, crazy d orbitals, all that stuff. That's all true as long as that atom is just all by itself, hanging out. Things change when they start to form bonds and they start to share. If we take methane, for example, so methane is a carbon and 4 hydrogens. If we write out carbon's electron configuration, and let's actually write the orbitals for this. So we have 2s, 1, 2, 2px, 2py, 2pz. So based on that, how many places does it look like carbon could share? How many orbitals could it share? 2. It looks like it could share with a little hydrogen that's got a 1s here, and it could share there. But we know that carbon bonds how many times? 4. It's the basis of most of life on Earth, the fact that carbon bonds 4 times. This is hugely important. So how is this possible? Well, what happens? What's a hybrid? Let me ask you that. And this is a question that 10 years ago students didn't have as ready an answer for, but now we have hybrid cars. So what's a hybrid? You don't have to be right, and you don't have to be technical. A mixture of 2 things, and that's actually a great definition, yeah. A hybrid vehicle is a combination of an electric power source and an internal combustion power source. Hybrid species are combinations of 2 different species. The eastern coyote, the coy wolf, is one of those. So a hybrid is when we combine 2 things, and the product of hybridization is something that's neither one nor the other. It's neither fish nor fowl. It's a new thing. So what happens with these orbitals is they actually sort of rearrange and merge themselves. With carbon as our example here, there are 4 orbitals here. There's only 1 s, but then there are 3 p's. There are 4 electrons. These sort of merge and combine, and what we end up with is, rather than one lower energy orbital and then 3 that are slightly higher, we end up with 4 hybrid orbitals, each composed of a little part of S and 3 parts, 1 part S to 3 parts P. So let's look at just some basics. So in that example, we end up with what's called an sp3 hybrid. Well, an sp3 is made up of, okay, you're going to love this. This is real creative. 1 s orbital and 3 p orbitals. We also have something called an sp2 orbital. Guess what that's made up of? 1 s orbital, 2 p orbitals. Ooh. Ooh. We have things called sp1 orbitals. You'll never guess. 1s, 1p. Now, I don't expect you to know a lot about hybridization. And I have to go back and review the new chem standards. I think this is kind of skimmed in the chem standards for high school for this course. What I have heard is feedback from students. I just had a student who had just taken chemistry at Ohio State last year, and he said, yeah, most of my first year of chemistry was pretty much a walk. It was all stuff we had done. I was helping other people. He said the one thing that we did in a lot more depth was hybridization. So I want you to be aware that it exists. I want you to be aware that this is what allows all of the geometries that you've just created. So if you can form 4 equal energy orbitals that are sp3, suddenly that allows you to make something that's tetrahedral. That's what allows it to bond in 4 ways identically. So sp3 orbitals, we would have 3 orbitals of identical energy. What would something that was bonded to 3 things, what shape would that take? Three things? Try trigonal planar. So sp2s give us trigonal planar geometries. That's really what I want you to be aware of. I'm not concerned that you can do a whole lot with these. If you are going on to take chemistry at the college level, which many of you in this class actually are, you'll do a lot more detail about orbital hybridization when you get there. So these are images of hybrid orbitals. We take this nice little spherical beach ball, and we take these weird drumstick, dumbbell, whatever you want to call them things, and when we merge an S and a P, we get this thing that allows for a bond that forms, off to one side of the nucleus. Hybridization makes possible linear molecules. Trigonal planar molecules. And what did we say that sp3s enabled? Tetrahedral. Yep. So, yeah, the tetrahedral. Because the sp3, you have 4 things that you can now bond to the central atom. If you can bond 4 things to the central atom, suddenly you've got a tetrahedral molecule. We will stop there for today. We'll pick up with intermolecular forces tomorrow. You've got the rest of the time to work on the labs, work on the questions, look over anything else in the chapter. Your test is going to be Friday. These labs are due Thursday. This test is all of Chapter 6, and as we look back, we did a lot of stuff in Chapter 6. You've got bonding types, electronegativity differences, molecular and ionic bonding, properties of ionic and molecular compounds. So you want to review a lot of that stuff. And like I said, I'm here for tutoring tonight. And if you guys are all done with the lab itself, right? Every single group? Awesome. Okay.